Okay, السلام عليكم شباب.
وعليكم السلام.
So we're still are focusing on the mechanical or the single effect evaporation system. And last time we have made a description for the single effect mechanical vapor compression system, which actually has some unique features, which is being a standalone unit. Don't need a boiler, you don't need a power plant to connect to. All you need is a compressor. So that looks like a very good option for operating this unit. There's a couple of, or there's just one drawback for it, which is that the energy consumption is a little bit on the high side if you compare it with well-known technologies for that utilize mechanical power as input, like the reverse osmosis system, for example. For an RO system, you can have a system that has definitely less power consumed compared to this one. Remember, for this one, we are not measuring the power in terms of performance ratio, because we are not relying on steam from an external source. You know, the performance ratio was basically the mass flow rate of the distillate that we are getting divided by, or per unit mass flow rate of steam. For this system, this is not the case. The kind of input energy you put is mechanical power. So we can evaluate it in terms of performance, like what we do for RO system. Like, for example, how much would be the power consumption, specific power consumption, which is how much kilowatt hour per cubic meter of the water. So that's the way we are looking at it. And in that sense, it is higher in performance compared with the RO system. And it needs sort of a breakthrough. It needs some sort of a way that people can reduce the amount of energy that can be given to the system so that you can get a decent amount of water and it becomes comparable. This is the drawback. Other than that, it's a compact system, it's a reliable system, and as a matter of fact, also it's a system that can operate on renewable energy. I mean, for example, you can have a set of PV panels, and the PV panels are generating electricity, and the electricity is feeding the compressor that runs the unit. So this is a possibility that can occur. Wind energy is another option with batteries to store the energy, and so on. So there are ways that we can operate this system relying on renewable energy. However, still the major problem that we are facing with it is that it has relatively high energy consumption. I had a master student, his name was Saddam, that was several years, maybe 4 or 5 years ago or so, where his master was on a system like that, on a multi-effect desalination system with mechanical vapor compression. And we came up with a new idea that we thought it's worth to be disclosed, and we patented already. The patent has been published in maybe previous summer or so, if I'm not mistaken, or the summer before. I just I lost track of the time where this patent was published, 2019 or 2020, which has an idea of maybe helping reducing the power requirements by adding another compressor that is going to compress an additional amount of vapor so that you have more vapor to condense, which means that more water to be produced, and that it really realized a reduction in the power consumption, but it's not significant, which means that still something that needs to be done here to reduce the power consumption. So we talked about this, we talked about the major components of the units, and what is different here is that we have a mechanical compressor, as you can see here. We do not have a condenser because we don't need to. What we have basically is a couple of heat exchangers that can be used as energy recovery to preheat the seawater, which is represented by the blue lines here. Seawater is distributed not equally to these heat exchangers in a way that we are heating the seawater from T cold water to TF, which is the feed temperature. To do the heating, we are taking some of the product which is being delivered at relatively high temperature, so that we cool down the product by heating the seawater, and the rejected brine, which is at considerably higher temperature, we reject it again through a heat exchanger so that it rejects the heat here to preheat the feed. So both of these streams, the desalinated water and the rejected brine, are cooled down to a temperature of T0, whereas the seawater is heated up from T cooling water up to a value of TF feed temperature. And then as it comes in here, it will be sprayed on outer surface of tubes where steam is passing inside. So it will reach to the saturation temperature, part of it will evaporate. The vapor is going to go through a mist eliminator to prevent the droplets that are entrained by the vapor to pass into the compressor, so that you make sure that whatever is coming here is pure vapor. The vapor is compressed on the compressor into superheated condition, and then it enters to the tube. First, it will desuperheat, it will lose sun sensible heating, and then it will condense, so it's lose the latent heat, and then after that we collect it as a product and we use it for preheating the feed before we put it in a product tank. The sprayed seawater will be heated to the saturation temperature, part of it will evaporate, and the rest is going to be rejected as brine. So when you look at the idea of the work, we have realized energy recovery, we have made a compact system. The only thing that needs to be looked at, and it's not a simple thing, I mean, it's something that needs substantial thinking and probably changing the kind of design the system is being done to reduce the power consumption. The compressor and evaporator are normally packed as one unit, and that helps make it the whole unit compact as well in size. Components of the evaporator remains the same. The heat exchangers are basically sort of either shell and tube heat exchangers or plate heat exchangers. And the benefits are being given here that the cost is not too high. Mechanical operation of the systems means something which is reliable. So the unit is expected to have long lifetime. The intake and pre-treatment processes are simple. It has horizontal film tube configuration, which results in high heat transfer coefficient for the condensation case. And accordingly, you would have effective heat transfer in the evaporator. Again, we'll have the same limitation of the single effect or even multi-effect evaporation, that the top brine temperature or highest temperature of the seawater which is sprayed should not exceed a value of 60 to 65 degrees centigrade to reduce the effect of scaling on the outer surface of tubes. We said for other desalination systems where heating can occur while seawater is inside the tubes, you can clean it by what we call bowl cleaning. But that does not apply here for this system, because simply scaling is occurring on the outside surface of the tubes, not inside. And hence, if you need to clean the tubes, you have to shut it down, you have to take the tube bundle outside, clean it, or replace it by another one. And this is a process that requires shutting down the plant, which means that you cannot do cleaning while the system is in operation. And that puts a limit on the top brine temperature to 60 to 65, although lately there have been attempts to do better pre-treatment of the seawater, either through nanotechnology or through graphene oxide or reduced graphene oxide coating on ultra filters, and that would segregate out the sulfates, the carbonates, the magnesium dioxide, and accordingly the problems of scaling can be reduced a lot, and that would encourage us to increase the temperature from 60 to 80 or 85 degrees centigrade. What's the benefit of increasing the temperature? Last time when we were looking at the performance measures, we have seen that the performance measures are not improving as we increase the top temperature. But the benefit is that we have a bigger flashing range or a bigger temperature difference between the top brine and the bottom brine temperatures. And then you can use more effects. More effects means better production and more water to be produced for the same quantity of steam. So it means higher PR or higher performance measures, lower specific energy consumption per cubic meter of water. The system is modular, which means that you can do it for a small scale or a medium scale. So it's not only something that has to be with very large scale production, as we will see in the MSF or MED systems. It's evaporating, and evaporation and condensation would mean that we are eliminating the salt. So we're talking about very pure water that's going to be produced. Actually, it is so pure that we have to have minerals so that it becomes suitable for our health to consume. We talked about some of the work that has been done earlier with mechanical vapor compression. And you can look at the numbers here, talking about currently the specific power consumption is around 10 kilowatt hour per cubic meter. This is a little bit on the high side, especially that now people are thinking of about 4, 3, maybe 2 kilowatt hour per cubic meter. So talking about 10, this is relatively a high value. Size of the, of the unit is not huge. We can talk about systems that can produce 2,500 or even 5,000 cubic meter per day. And this is not so huge, but it's good enough for medium-sized communities. Not too much units are available in the industry, but still it has its own merits, it has its own benefits to have a system which is operating like this. This is a layout of the system here, and you can see it's one unit. This is the compressor here, and this is the evaporator. And what happens here is the vapor passes through the tubes, that it comes here in the core of the evaporator, where it will be sucked into the compressor, and then it will be compressed, and it will be given here at both ends, where it will pass basically the vapor inside the tubes, and then it would operate in a way that it heats the sprayed water and evaporates part of it. Then we have 3 colors at the bottom here. We have a heat exchanger. This is the heat exchanger, this one. And the heat exchanger here is, the good thing is about the heat exchanger is that it handles 3 fluids. The 3 fluids are, we have rejected brine, which is the yellow one. So the rejected brine is entering into the heat exchanger. And while it's passing through the heat exchanger, it heats the feed water which is coming in. The feed water is the green line. So we have a pump that gets the supply water from the sea, and the green line here is being preheated in that heat exchanger before it is admitted to the spraying system of the unit here. Actually, in this specific layout, it is mixed with the brine, and after that, the whole mixture is being taken to be sprayed at the top. We have a brine recirculation this way, and we reduce the amount of additives that should be given to the seawater. And the third kind of flow regime here is for the desalinated water or the product water. This is the yellow, this is the blue lines here, which are also passing by the heat exchanger. So the heat exchanger is making use of hot distillate water, hot rejected brine, and cold seawater. So they heat the seawater here, and this is all being done here in one heat exchanger, not 3 as we have seen, not 2 heat exchangers as we have seen in the previous figure or the sketch that you have seen earlier. These are some layouts that are now in the industry for the single effect mechanical vapor compression system. So they are given by different companies, but the idea is the idea. And again, this one is doing like a heat exchanger for this one, which is taking the 3 fluids in, the fresh water, the hot fresh water, the hot brine, and the cold seawater are all passing in here so that exchange of heat can occur, and the seawater is being recirculated here upon mixing with the fresh seawater, so that you are making use of the pre-treated seawater there. And this is an industrial unit. It's a photograph for that unit here. And again, a sketch of this unit, another photograph of a small scale unit, which is found here. This is the temperature profile that we have inside the evaporator. Last time we have gone through the equations of the balance for this system, so we don't have to repeat it today, except for pointing out at the expression that we use for evaluating the work done for the unit. The compressor has, at the delivery part, superheated steam. The superheated steam at TS enters into the evaporator. First, it will de-superheat from TS to TD. And if you recall from last time, we talked about a certain temperature difference between both of these, which is in the order of 3 to 5 degrees centigrade, maybe less. And then, so de-superheating and then condensation occurs to a temperature of TD, temperature of the distillate or the condensate distillate that leaves the unit. And the feed seawater is coming at TF. It increases in temperature by spraying over the hot tubes to the TB, which is its saturation temperature. And then as the vapor forms, the vapor is at a temperature TV less than the value of TB by the boiling point elevation. And not only the boiling point elevation, but if there is a pressure loss across the demister, it is accompanied by a temperature reduction as well. So there are a couple of elements or a couple of reasons why the temperature of the vapor that leaves the unit is leaving at less temperature compared to TB. Part of it due to the boiling point elevation, and the other part is that as your vapor is leaving through restrictions, there is a little pressure drop which is associated with a temperature drop as well. When it comes to the heat exchangers, the feed preheaters, you have distillate leaving the unit. This distillate is losing heat in the heat exchanger to the cold or to the feed seawater coming in. There is a rejected brine, which is losing heat to the seawater coming in. Both of them are adjusted to leave at a temperature T naught. And this is an arbitrary thing. It's not a must. And the cooling water is being heated because of receiving energy from both streams. This can be done in one heat exchangers or two heat exchangers, but the idea is to preheat the feed from T cooling water up to TF. These are typical numbers that we would like to maintain. For example, the temperature difference between TS leaving the compressor de-superheats in the evaporator to TD. This temperature difference is somewhere between 4 to 10. The lower would probably require more high heat transfer area, but the lower temperature difference means lower entropy generation. So it's a trade-off. You have to think of, I need to have high temperature difference so that the high temperature difference reduces the required area, but I need low temperature difference because I need to avoid the generation of entropy. So you have to optimize or make a balance between these two opposing effects. The difference between TB and TF is 1 to 5 degrees centigrade, which means that as the seawater comes in, it needs to be heated by spraying it on the outside surface of the hot tubes, and it heats from TF to the saturation temperature. This temperature difference is somewhere between 1 to 5 degrees centigrade. In the example we solved for the single effect evaporation early, it was 5. Remember, the T feed was 70 and the TB was 75. So temperature difference was 5. Temperature difference between TD and TB is 1 to 5 degrees centigrade. This is TD and this is TB. So this is basically the heat transfer which is occurring inside the evaporator. Tubes having steam which is condensing at TD, and seawater which is being heated up to the boiling temperature TB, or the brine rejected temperature TB. The difference between T naught and T cooling water, this is in the feed preheater or the heat exchangers, and we do this limitation so that we just have to consider the area needed in the heat exchanger. Here I'm talking about the temperature difference between T naught and T cooling water. Again, the higher the temperature difference, the smaller the heat transfer area, but the higher the temperature difference, the higher the entropy generation, and the less effective the unit becomes. We talked about the balance equation last time, the mass balance, which is always there in every conventional desalination system, that the feed is being split into desalinated water and rejected brine. Salinity of the rejected brine is 0, so that when you write the salinity balance, then MF XF is M dot B XB. Actually, when we come to cover the RO system, the RO system does not give pure water. It gives water with certain salinity. And for that sake, when it comes to this this equation in the RO, we have to say here plus M dot distillate X distillate, but not for the thermal units because the distillate is free of salt. Equations 3 and 4 are nothing but manipulations or rewriting of equations 1 and 2. We looked at the energy balance for the two heaters together, and then the two heaters are being splitted. Part of it is energy balance lost by the distillate and energy balance lost by the brine. And all of these two streams are used to preheat the feed, M dot feed, from T cooling water to TF. This green equation is not needed. This is just for the sake of writing a closed form formula. You bring in T naught all in one side and all the rest in the other side. I mean, there's no, it's not really that important to write that equation, but I would rather prefer that we go through the analysis in the same way that we are doing it here. The evaporator has a high side, which is the steam coming in. The steam has to lose its superheat first. So sensible cooling for the steam, M dot distillate, Cp of the vapor, Ts minus Td. This is the sensible cooling of the steam from T steam to T distillate. And there is condensation, which is M dot distillate HFG. This is basically what is happening here. There's a loss of sensible energy here, M dot vapor, Cp of the vapor, Ts minus Td, which is the sensible part. And then this part is the latent part, which is M dot distillate multiplied by HFG at Td. And on the other side here, we have feed, which is being heated sensibly. So M dot feed, Cp, Tb minus Tf, plus the M dot vapor multiplied by HFG at Tb. And these are the two equations that are taking care of the energy balance inside the evaporator. This is the fluid in the hot side, steam inside the tubes, and which is the lower equation. The upper equation is heating the feed sensibly from T feed to T brine or T boiling, and part of it is going to evaporate. Simplification is not crucial to us. You don't have to go through it. You just maybe read it once or twice. And then when it comes to energy balance, then these are the kind of energy balance equations that we have. In this equation, we have neglected the effect of desuperheating or heating of the feed, the sensible part here and the sensible part neglected. We assume that Q is equal to the overall heat transfer coefficient into the area, into the temperature difference Td minus Tb. If you want to be very accurate, then this part should be treated alone and use the log mean temperature difference. This part should be treated alone and use the log mean temperature difference if you just want to be more accurate in estimating the area. And then for the two heat exchangers, then these are the energy balance for the heat exchangers. One of them is using the brine as a source of heat. The brine cools down from Tb to T naught, heating part of the seawater, which is 1 minus alpha, from T cooling water to T feed. And the log mean temperature difference here is given by that expression. Whereas the other heat exchanger is heating alpha m dot feed from T cooling water to TF by cooling the distillate, m dot distillate Cp T distillate minus T naught. And it is equal to U distillate into area distillate into the log mean temperature difference of the distillate heat exchanger. Specific heat transfer area is all the areas that we have, area of the evaporator, area of the two heat exchangers, divided by m dot distillate. So that gives how much heat transfer area is needed per unit productivity. The specific power consumption, this equation has been borrowed from thermodynamics 1, that the specific work is equal to gamma, which is Cp over Cv, the pressure and specific volume of the intake divided by efficiency of the compressor, gamma minus 1 into the pressure ratio to the power gamma minus 1 over gamma, whole minus 1. That gives us the value of the specific power needed for operation of this system. Any questions in the mechanical vapor compression system? If not, then I'm going to share with you the idea of another single effect evaporation system. And it's not widely spread, but it is used and it has a good potential in the sense is that it does two things at the same time, like the idea of a combo. You go for a sandwich of burger, then you can get either the sandwich or sandwich plus fries and Pepsi. So it goes like that. What's the idea here? If we can do a couple of things, or if somebody is hungry, I'm sorry, actually I haven't got my lunch yet. The point here would be related to if you are going to buy like a kitchen machine, then you can either buy the blender alone, the mincer alone, or maybe you can get them all to be installed on one engine or on one motor. The idea here is combine a couple of units together to produce something. From the thermodynamic point of view, remember, you have studied the cogeneration cycle, in which you have a gas turbine cycle on the top with another bottom cycle, which is a steam turbine cycle, a Rankine cycle, and both of them are operating together. Or what we just mentioned of the idea of having a desalination plant like MAD or MSF or even single effect evaporation system, which is connected to a power plant. So you are producing power and producing water. This model of producing power and water exists around us. If you go to Al Aziziyah and Khobar, you'll find SWCC, MSF units there and power plant, steam power plant. The same thing for SWCC plant in Al Jubail. Marafiq have the three. They have gas turbines, steam turbines, and MED desalination system. So having a system that can operate to produce more than one output is not new. It is something which is even. People are moving in this direction recently. What we see in front of you here is a layout of a single effect absorption vapor compression system. It is basically having two effects. One of them is a cooling effect. You need to air condition a certain place. You need to air condition a cooling zone, for example, which could be a building or so. And you need to get desalinated water at the same time. So what you do, you combine an absorption system, which is basically made up of an absorber and a generator, some heat exchanger, which is there, and this unit is to be attached to a water desalination system. The absorber unit here is going to do something that will help us for the single effect mechanical system or the single effect evaporation system, which is, if you remember, I said one of the problems that we have with the mechanical vapor compression system is that the mechanical power by the compressor is substantially high. And that would make the industry generally is not fond of, they are not like fans of the single effect mechanical system because of the high power consumption. So why is that? Because we are using a compressor, and the compressor is compressing vapor, and the vapor usually has high specific volume. You know that for steady state, steady flow processes, the work is given by the volume multiplied by delta P. If the specific volume is high, then you are talking about substantially high energy needed to run the unit. It's not like pumping water. Pumping water is specific volume for the water is 0.001. So it's a small value. When you multiply that by delta pressure, then the total power for the pump is not high. But not for a compressor, because simply the specific volume of the vapor is high. So how can we compress the vapor without a compressor? This is what we are looking for. And the idea here came by using this kind of absorption compressor. It's called absorption vapor compression system. What's the problem? You need to avoid compressing the vapor from low pressure to high pressure because it's going to consume lots of energy. Fine, let's do something. Let's take this vapor and bring a fluid that's going to absorb the vapor. The fluid basically is lithium bromide. So what you are going to do, you are going to get the vapor, which is generated in the unit here, and this vapor is going to be absorbed by lithium bromide solution. And then you are going to compress the lithium bromide solution using a pump to a high pressure. After you do that, you are going to heat that diluted solution so that the vapor leaves, and then you have vapor at high pressure and temperature. So it's as simple as that. Instead, or try to avoid direct compression of the vapor. So what you do, you are going to absorb this vapor by a fluid, a liquid. Then you pump the liquid, and after you pump the liquid, you add some heat to evaporate the vapor, and then you take the vapor at high pressure and temperature. Again, let me stress here that the main point that I mean here is coming up from the idea of the compression for steady state, steady flow process. The work is minus V dP integral. If I'm talking about a specific volume, or let it be like that. And let's talk about water, for example. The specific volume for liquid water is 0.001 cubic meter per kilogram. Specific volume for water vapor is in the order of 1 cubic meter per kilogram. It's 1,000 times the specific volume of the liquid water. So here you are talking about either to put a value of 0.001 and put a value of 1, which means that the work can be several orders of magnitude higher if you are compressing gas or vapor. It's much higher than the work needed to compress liquid. And this is the basic idea. Instead of using a compressor, we try to use a pump. Why not the compressor? Because the power consumption is too high, whereas for the pump, the power consumption is low. But we need to compress vapor. So what we do, you convert the vapor into liquid, not by condensation, because this requires lots of heat transfer. It is by absorption. And there are some famous units for absorption. Lithium bromide is one of them. Lithium chloride is another one. Calcium chloride is a third one. So you are talking about different components, different candidates, liquid candidates that are eager to absorb water or water vapor. They can absorb the water or the water vapor, and then instead of having a strong solution, the solution becomes weak, diluted solution. You pump the diluted solution using a pump with less power to a high pressure and definitely high temperature, or even if it's only high pressure. And then what you do, you heat it up. You heat it up with low grade heat. So it can be solar, for example. You can get solar collectors to heat the diluted solution, and then the solution becomes, after dilution, vapor is going to form. The vapor will leave the regenerator, and the strong solution is going to go back again to the absorber, and the cycle repeats itself. So we are going to get this and combine it with a refrigeration system, and then we are getting all benefits out of this. I'm going to share with you again this slide, which is talking about the layout of the single effect absorption system. Let me bring it here to the presentation mode. Yes. Oh, sorry, there's something that happened here, which is I need just to duplicate. Yes. So I would share it then. Okay. So here's the system again. We have the single effect evaporation system, which is this. And we have the absorption system, which is that here. Seems that the mouse is not just obeying what I needed to do for this. So what would happen here? We have this absorber and this generator. In the absorber, what happens? I have a strong solution of the lithium bromide, for example. Lithium bromide, when you have water coming into it, what would happen? It's going to absorb the water, and instead of having a strong solution, it becomes a weak solution. The absorption process is generated with heat transfer. Normally, it gets heated. So that's why we are using cooling water to keep its temperature low. Then you take this diluted solution and you pump it. And while you are pumping it, you are preheating it by passing it through a heat exchanger. The heat exchanger is going to preheat it, and then it will be sprayed here. When it is sprayed here, you are basically allowing for heat addition to this unit. The heat addition, what does it do? It heats that diluted solution so that the vapor leaves from the top, and the concentrated solution, which is hot, leaves at the bottom. That's why while it is leaving, before reaching to the absorber, you have a heat exchanger here for preheating that feed, which is so this is diluted solution that's going to be preheated before being sprayed. And this is a condensed solution, which is going to be cooled in that heat exchanger. After that, you pass it by an expansion valve so that you can bring it to the low temperature level here. So there's a low temperature level of the cycle, and there's high temperature, low pressure level and high pressure level. They are separated by an expansion valve here and a pump here. Expansion valve for the strong solution so that you can expand it to lower pressure and lower temperature. And there is a pump that will take the diluted solution and pump it to a higher pressure, to the high pressure side here. Preheated and then sprayed. When it is sprayed, you have a heater or a solar collector system, or you have heat rejected in a certain stack or chimney of a process heat or whatever heat, which is going to be otherwise rejected to the surrounding. The vapor that comes here is the one that we use as a source of heat to the desalination unit. You needed heating anyway for the cooling system. So you made use of that heat to generate vapor, but you did not throw the vapor away. You took the vapor to be the source of heat for the desalination unit. What does it do? It's going to take the seawater here, which is sprayed on the outside surface of the tubes. It will be heated to saturation temperature. Vapor will form. You take the vapor, you condense it, and then this is your product. Meanwhile, the vapor that has entered here, it will condense inside the tubes. You take the condensate, you expand it to low temperature through an expansion valve, and then you pass a heat exchanger here, or you pass water through a system here that takes that cooling effect to the cooling zone for air conditioning. So you have a system for air conditioning, and you have a system for water desalination at the same time. What I'm going to do, I'll be sharing a paper that we have done. It has the detailed analysis of this unit, and it has the mass and energy balance of each component. So I'm going to put it in Blackboard so that you can have a look at it and see how the whole system is performing.
Excuse me, doctor.
Yes, go ahead, please.
Can you explain the core difference between absorption and adsorption system?
The main difference is that absorption, when we are using the letter B for boy, it means that you have a liquid. This liquid is absorbing a vapor, and the liquid is being diluted. Okay, so the vapor is going to melt inside inside the liquid, and it becomes like a homogeneous solution which is diluted. So the whole volume of the liquid has worked on absorbing the vapor to it. On the other hand, adsorption with the D, it is a surface process where you have basically some sort of a solid material that can adsorb some of the vapor on its surface. Examples are like silica gel, and silica gel adsorbs water vapor on the surface, and then you can take the silica gel, you can put it inside an oven where you can regenerate it back again. The oven is going to generate the vapor. You take the vapor out, you can take this vapor and put it into a desalination unit like what we're doing here. But the main difference here is that there is something which is occurring for the whole volume. This is what we see in front of us here. On the other hand, silica gel as an adsorber is absorbing the vapor only on the surface. Not only silica gel, but lately there have been a family of MOFs, which is metal organic frameworks, that are being used for generating cooling effect through adsorption. And we have done some work even for doing adsorption and connecting it into a desalination system. We have a student that defended his master last semester, and he was basically doing a combination between adsorption and MED system. And there is another famous system that has been built in KAUST, where Dr. Neg and Shahzad Wakil have basically got a grant. They built a system. The system, they call it MEDAD. The word MEDAD stands for MED, multiple effect desalination, plus AD, adsorption system. They did not do cooling effect there. Their target was basically for desalination, but it can be done for both of them. And this is what Hassan Al Khalifa did in his master that he defended last semester. He also used metal organic frameworks, which are superior in performance compared to the silica gel, but they are a little bit expensive. So when it comes to the economic process and whether it will find a place in the market or not, we're just waiting for the prices of the metal organic frameworks to be reduced so that it becomes competitor in the market. Did I answer your question for the difference between them?
Yes, doctor. Thank you. Thank you.
Okay, you're welcome. By the way, the metal organic frameworks, one of them is called HKUST1, which is the word HKUST stands for Hong Kong University of Science and Technology, which means that it's a unit that has been totally devised inside the University of Hong Kong, and it has been declared as a potential adsorber. The only problem with it is that it's not stable with water at high temperatures, and this is the only drawback that they have on this system, which means that you have a limit on temperature operation for this unit, but there are other alternatives to it that are available in the market and can be used. Okay, so this is about the single effect evaporation. As you see, in terms of analysis, whether it is single effect evaporation or single effect evaporation with thermovapor compressor, the TVC, or thermovapor or mechanical, or sorry, or single effect evaporation with mechanical compression, mechanical vapor compression, the principles are basically the same, but it's an enhancement in the operation with the TVC, and it's an alternative way to compress or to generate steam using the MVC system. But in terms of analysis and energy balance, it's the same principles with slight differences here and there. What I'm going to share with you now is the next step. After working with single effect evaporation systems and seeing the drawbacks, you have to reject both brine and distillate at relatively high temperature and not make use of them. Why don't we do that? Why don't we use these units? Using the units here, it means that we are going to make use of these streams. So the brine which is leaving a unit is not going to be thrown away, but we are going to make use of it. And this is basically what is it that I'm going to talk about in our next topic, which is basically multiple effect desalination system. Let me share the screen with you, and then you would be able to see that. Sorry, it's again the issue because I'm using two screens, so they do it as an extension. Although I need to have a single screen. So what do you see here? Let me fix it again just to make it as a duplicate. So multiple effect evaporation is what we need to consider now. So what does it do? What's the main difference? The main difference is that it includes several evaporators, not a single one. And the title said that the previous one was single effect evaporation. This is multiple effect evaporation. Who remembers what was the PR for the single effect evaporation? Do you have the number still in your head? Performance ratio in the example that we have solved. Anyone remembers?
I think, Doctor, 0.97.
Yes, exactly, which means that it was close to a value of 1. What does this mean? It means for every 1 kilogram per second of steam, you are producing almost 1 kilogram per second of distillate water. Okay, 1 kilogram per second of steam inside the tubes, it will condense, give the latent heat, and this latent heat is going to produce 1 kilogram per second of distillate. So the distillate which is leaving at as a saturated vapor, if we take this distillate and put it as a source of heat for the next effect, it may produce another kilogram per second of vapor, almost. If we take this and put it inside the tubes of the next evaporator, it might produce something close to 1 kilogram per second of vapor. So the point here is we are reutilizing the vapor that we have. We need to condense the vapor. Okay, and instead of condensing it in a condenser, why don't we condense it in an evaporator and generate additional amount of vapor, which is almost equal. It's a little bit less because as you are moving from one effect to the other, both pressure and temperature reduce. But it's not only the temperature that reduces, we're also reducing pressure. Reducing the pressure, it means that the saturation temperature drops. So boiling still can occur. That's why sometimes they call it either multi-effect distillation, and sometimes they call it multi-effect evaporation, or even multi-effect boiling, because in each one of the effects, the vapor leaving one effect is going to condense in the next one. So if you have 3 effects, then for 1 kilogram per second of steam, you are generating 3 kilogram per second of water. If you have 10 effects, 1 kilogram per second of steam can produce 10 kilogram per second of distillate water. Not really 10, because you have seen here that for 1 kilogram per second of steam, we are getting 0.97 kilogram per second of vapor. If you have 2, then the second one will give like 0.92. If you have 3, the third one would be 0.9. The fourth one would be 0.88. So when I'm saying that I have 5 effects, I don't really expect 5 as a value of the PR. It could be 4 or 4.1.2. It depends on the system that I have. But anyway, you are generating multiples of kilogram per second of vapor per single kilogram per second of steam to be used. And here comes the issue of having units with high performance ratio. The MED systems, as you see, theoretically speaking, you increase the effects by 1, you increase the PR by 1. Theoretically speaking, it's a little bit less than 1, but anyway, approximately this is what we're saying. So if you have a system of 20 effects, the PR will be 20 or so. But we cannot have 20%. Why? Because the top brine temperature here is about 65. This is the maximum temperature we can increase the seawater to. Why? Because of scaling. Otherwise, scaling is going to occur and you cannot operate the unit effectively. Scaling is going to form. Scaling, it means a layer of insulation would be there. The heat transfer from the steam to the seawater is going to reduce, and accordingly, you are not going to produce enough vapor. So we have to limit it with a maximum temperature of 65, and the bottom temperature should be a little bit higher than the seawater temperature. If the seawater's temperature is at 30, then you make your bottom temperature 40. So the temperature or the flashing range, the range of temperature from the highest top brine temperature to the lowest bottom type brine temperature is from 65 to 40. So 25 degrees centigrade. If you have a delta T per effect as 3 degrees centigrade, then you have 8 effects. And this is typically the market now. You can find units always with 8 effects. In El Jubail, there is Marafiq, water desalination plant. Actually, it's some sort of a private sector or semi-private sector plant in which it is producing electricity and water, selling the electricity to Saudi Electrical Company, selling the water to National Water Company, and this is how they make their profit. This system of Marafiq is basically having 27 desalination units. Each one of them is 8 effect, multiple effect desalination system, which means that 8 is the typical value for the industry. Can we have it 10? Can we have it 12? Yes, we can. If you are able to do nanofiltration or reduced graphene oxide ultrafiltration to the seawater coming in, then you are able to eliminate the ions that result in scaling, and then you can increase the top brine temperature without fears. When you do that, instead of having 8 effects, you can make them 10 or 12. So instead of having a PR equal to 8, the PR can equal to 12, can equal to 16, depending on what temperature that you are going to reach. So what I want you to remember from here is, for MED system, theoretically speaking, the performance ratio is directly proportional to the number of effects. You need higher performance ratio, increase the number of effects. This is not the same as in the MSF. In the MSF, it is not proportional to the number of effects, which means that you can have an MSF, which is typically in the market having somewhere between 19 to 22 stages, and the PR is limited to 9.5 or 10. That's it. Classification of the multi-effect desalination system depends on how the seawater is going to flow within the system. Seawater can flow from left to right, from right to left, or from up to down. And each one of them has a certain title. So we have the forward feed, it's going from left to right, or actually it is going in the same direction of the vapor. And you will see that in the figure. Backward, which is the opposite, or going going basically parallel, which is basically going perpendicular to the direction of vapor flow. The difference, or this nomenclature, is related to how the vapor and how the seawater flowing directions are going to be the same, opposite, or normal when you look at the system. This is an example here of what we call a forward feed MED system. Look at the forward feed MED system that we have here. And let's start from the right here. This blue arrow, this is the seawater into the condenser. The condenser is receiving vapor from the last effect. The vapor will condense into sweet water, which is going to join the product line. Whereas the seawater passing inside the tubes is going to receive that latent heat, and it will be preheated from T cooling water to TF. TF, or the feed temperature seawater, is going to go through all the way to the first effect, effect number 1. And then it will be sprayed on the outside surface of the tubes, as what happens in a single effect evaporation exactly. Part of it will evaporate, and the rest is going to be rejected as brine. The vapor that will leave the first effect is going to enter to the second effect inside the tubes, where it will condense. The brine which leaves the first effect is going through pipes here to the second effect to be sprayed on the outside surface of the tubes. So it will be heated up to the saturation temperature, some vapor will form, and the rest is going to be rejected. The formed vapor is going to go to the next effect to condense inside the tubes into product. And the product here is going to be collected. We did not collect the product coming from effect number 1 because this is steam that we are getting from a power plant, and we have to return to the power plant again. So this steam does not belong to us. Whereas the vapor that has formed here, this belongs to us. This is vapor generated from the seawater which is being sprayed. So it will enter here, and when it condenses here, then this basically is the first quantity of our product as sweet water. And it will join, or it will be joined by another quantity which will condense in the next evaporator, and another quantity that will condense in the next evaporator, and the quantity that will condense in the condenser. All of these, this one, this one, this one, this one, 4 of them are making the product sweet water that we have. Why 4? Because we have 4 effects. So keep on remembering that. First effect is receiving steam from an external source, a boiler or a power plant. So after condensing, the steam should go back to that source. Whereas starting from the condensate in effect number 2, this is our product. The vapor that we are getting here is the vapor that has formed in effect number 1. It will condense here, and then we are going to collect it as D1 right here. So we are collecting sweet water here and here. So this red line here is the line of sweet water production. What about the couple of black boxes that we have on the top here? These are a couple of heat exchangers. And the target, or the reason for using heat exchangers here is we'd like to preheat the feed. The feed has increased from T cooling water to TF, but we need to increase its temperature from TF to TF1 or TF2 or whatever. Why is that? Because the vapor, when it is sprayed here, it will first be heated sensibly to the saturation temperature before part of it will evaporate. If it comes at a higher temperature, then the sensible portion is going to be less and more vapor is going to be there. So it's going to help to recover as much energy as possible. How we do that? The vapor which is leaving this effect, not all of it is going to go to the next effect. Actually, part of it will go here to condense in the shell side of this preheater, and the rest is going to condense in the evaporator tubes of next effect. The part that will condense in the shell side here is going to give its latent heat to the feed which is passing here. So you are heating the feed. Ultimately, or ideally, you can heat the feed to the saturation temperature here. So any energy given by the boiler steam is going to work on evaporating it right away. As brine which is leaving here is leaving at relatively high temperature. When it comes to the next effect, it may not need to be preheated. It will be coming as saturated vapor, and then it will be evaporated right away by the vapor which is inside the tubes. So we have preheaters here, and the preheaters are additional sort of energy recovery, and the energy recovery here is working on increasing the temperature to TF to reduce the sensible heating which is occurring to the sprayed seawater that will be heated by steam coming from the external boiler. One more component here I did not talk about, which is the red box below here. This is what we call a flash box. Why do we need a flash box? The flash box basically is associated with the conditions in terms of pressure and temperature of that effect that it's coming from. Which means that this flash box here is at a pressure P2. This is effect number 1, this is effect number 2. So the pressure here is P2. But the vapor has formed here in P1. If we neglect the pressure losses, then all of this fluid inside the tubes is at a pressure of P1. So the pressure of the fluid here is P1. It is going to enter into a flash box tubes at a temperature and pressure of P2 and T2. You have a fluid, liquid, coming from high pressure into a low pressure. What will happen? Flashing is going to occur. So some vapor will form. You take this vapor up here to help in preheating the feed. It will condense. You collect all the condensate, the part that you took from the formed vapor, the part that you took from the flashed off vapor, and all of it is going to get back here again. So your performance in terms of numbers was not affected. You have retained all the quantity. You just use the vapor. Energy associated with the vapor, you convert it into liquid, and then you took the liquid to the productivity here. You did not really lose anything, but no, you gained. You made use of the energy as much as you can to preheat the feed, which is coming, and this is being done by using preheaters. The preheaters are fed by portion of the vapor formed in the effect, in addition to the flashed off vapor in the flash boxes. The question here again, why do we call it forward feed? The seawater, when it comes, all the seawater has gone to the effect number 1. And then when it leaves effect number 1, it goes to effect number 2. Then when it leaves effect number 2, it goes to effect number 3. When it leaves effect number 3, it goes to effect number 4. When it leaves effect number 4, it goes to the condenser. What about the vapor? Vapor is coming from an external boiler at effect number 1. The vapor formed in 1 will go to 2. So also the vapor is moving from 1 to 2, and then 2 to 3, and then 3 to 4, and then 4 to the condenser to condense there. So both the seawater and the vapor are moving in the same direction from left to right. This is why this arrangement here is called forward feed. It's going all from effect number 1 to the last effect, effect number n. Is that the only available layout? The answer is no. We have another layout here, which is backward. Backward means what? The vapor will always go from left to right. You get steam from the power plant, it will condense, You return it back again to the power plant, and then you have vapor. The vapor that will form here is going to feed the next effect. And then water will leave, and the vapor that's formed here is going to go to the next effect. So the vapor that you are producing as product, before you take it, you condense it, and while you are condensing it, you are making use of that by generating additional amount of vapor. So this is the vapor here is going to leave to move always from left to right. What about the seawater? Seawater here that leaves the condenser goes inside this effect, and part of it will evaporate, and the part that will not evaporate is going to leave to go to the previous effect. Part of it will evaporate, whatever will not evaporate or the rejected will go to the previous effect, previous effect, previous effect until it reaches to the first effect. So it's the opposite to the previous one. Previous one, everything has gone to effect number one, both vapor and seawater, and then it moved from 1 to 2 to 3 to 4. Here, the vapor is moving from 1 to 2 to 3 to 4, but the seawater is going from 4 to 3 to 2 to 1. Is there a problem with this layout? The answer is yes, there is a problem with this layout, which is, as you are moving from this effect number 6 to effect number 5, what happens to the temperature of the seawater? Who can tell?
It will decrease.
Going from here to here, remember that direction of the vapor is from here to here, and the pressure is reducing in this direction. So always, effect number 1 is the effect of highest pressure and temperature. Effect number n is the one with lowest pressure and temperature. So as the seawater is moving from 6 to 5, its temperature will increase. What about the concentration? You have seawater here,
Yes.
evaporated, and the rest is going to go here. So the concentration in 5 will be higher or
It's
lower?
going to be higher.
Higher.
Be higher than 6. And it will keep on increasing from 5 to 4 to 3 to 2 to 1. Now we are in trouble because we are increasing the temperature and we are increasing the salinity, which means that you can reach the saturation point soon. What is the saturation point? It is the temperature at which the salt crystals can be separated and stay on the surface, scaling. Scaling increases as the temperature increases. So this is basically the bad thing about this layout. That's why you can seldom find a backward feed operation system. Maybe it can be done for brackish water, for example, but not for salty water with high salinity of salt. Otherwise, the system is going to scale very quickly, and because we are doing the combination of high salinity and high temperature at the same time. The previous one, the salinity increases in this direction, but the temperature drops. So you are in the safe side. But here, that's not what's happening for this arrangement. So we have seen the forward feed, we have seen the backward feed, and before we leave, we can look at the parallel feed. Parallel means what? It means that the seawater that enters the condenser, it is gaining some heat from the condensing vapor, and it leaves at the temperature TF. This portion at the temperature TF is going to be distributed in parallel to every effect here. So in every effect, the quantity that enters here is entering at a temperature TF and salinity XF because of the parallel flow that you can see here. All of them are at the same temperature, all of them are at the same salinity, and we assume all of them also at the same flow rate. So m dot feed here is divided, if this is 4 effects, then this is F over 4, F over 4, F over 4, and F over 4. So this is the parallel feed here. And what also we may notice is that definitely it has one benefit, is that the vapor which is coming here does not have to preheat the whole quantity. It only preheats a fraction of it. If we have 4 effects, then basically you are heating 1/4 of the flow. So you may need less amount of energy from the power plant. This is one benefit. But this benefit, there's nothing free. This benefit is coming on the expense of something else. I hope somebody has noticed that. Because I just mentioned a while ago that the feed which is entering every unit is entering in parallel at the same TF and salinity. And as we are moving from effect number 1 to 2 to 3 to 4, the temperature reduces. Temperature of the vapor reduces. Would that mean that in every one of these effects, there has to be sensible heating? Note that for each effect, the saturation temperature is greater than TF. So heating from TF to the saturation temperature is step number 1. Then sensible heating, then latent heating of evaporation is going to occur. Meaning that if the feed temperature is, say, 40 degrees centigrade, and the saturation temperature here is 65, then it has to be heated up from 40 to 65, and then evaporation will occur. This one is at 62, so you have to heat it from 40 to 62 before vapor will start to form. You have to heat it from 40 to maybe 58. Here you have to heat it from 40 to 56, which means that in every one of these effects, sensible heating would start, followed by evaporation. That was not the same case for a forward feed, because on the forward feed, the brine leaving here is leaving at a high temperature. When it reaches here, it's almost saturated. And it leaves at a higher temperature, goes to the lower temperature area. Definitely there are some losses here, which means that slight decrease in temperature. So then when it reaches here at lower pressure and temperature, it will be also saturated. So the sensible heating in the forward feed occurs in the first effect only. But in the parallel feed, it occurs in every one of the stages. So we have got a benefit here by having to use steam from outside surface to heat only 1/4 of, or maybe 1/6 if it's a 6th effect, or 1/8 if it's an 8th effect system of the feed seawater. But in each effect, the vapor that I'm going to form will be first utilized to preheat the feed and then evaporating it, preheat the feed and evaporating it, and so on. So at the end, which one is better? I cannot answer it now. We have to do analysis to see which one is better. And the first quick answer is go to the desalination plants working on MED that are available in the market. You will find most of them are working on a parallel feed arrangement. So that tells that this arrangement is expected to be better compared to the forward and the backward feed. The details of each one of them is going to be the topic of our subject on Wednesday, inshallah. So remember, Wednesday we have quiz on the HDH system, and then we're going to continue also with this MED system configuration. That would be it for today. Any questions or comments?